Photosynthesis. Some may think it is a complicated process in which a plant magics food from nowhere, and others may think it to be a pesky chapter in the biology textbook that requires you to memorize weirdly long words such as this, and listen to your bio teacher rattle off an incomprehensible list of chemicals mixing with chemicals. However, after this video, you will understand how plants and some bacteria break down the universal solvent and give itself enough energy and food to sustain all the ecosystem in the world while giving us the oxygen we breathe. You will understand how an elegant system of light-induced chemical bashing could take this and turn it into this. Ladies and gentlemen, welcome to a simple guide through photosynthesis.
When you first learn about photosynthesis, it is likely you come across this equation: 6CO2 plus 6H12O plus light equals C6H12O6 plus 6O2 or 6 carbon dioxide plus 6 water molecules plus light equals 1 glucose molecule and 6 oxygen molecules. This is the fundamental and general chemical equation describing photosynthesis. It is important to start with the chemical equation for one simple reason: it lets us approach it from the chemical angle. We have a notion that photosynthesis is a complicated process involving as common concept as light, and a niche concept as a protein cluster to somehow turn sunlight into nom-noms. But let's abandon the notions that we have and objectively look at what the equation says. On one side we have 6CO2 and H2O. The two molecules have two characteristics in common. They are both the most common molecules on Earth that contain valuable elements for building organic molecules such as carbon, oxygen, and hydrogen. 2. They are both not very nutritious. Carbon dioxide and water are both molecules that release energy while created and need energy to break down. That's why water has 0 calories, and inhaling someone else's breath or the foams from a fire extinguisher aren't exactly the most healthy dietary choices. Therefore, the process of turning these two inorganic molecules into usable material will take a lot of energy, which comes to us in the form of light, providing us with the energy needed to fuel the entire reaction. On the other side of the equation, we have glucose and oxygen molecules. Glucose is an organic molecule rich in energy, which, whilst being broken down, could fuel any living organism. And oxygen is oxygen, a neatly organized group of molecules that happen to be the leftover of the equation. And there we have it. Photosynthesis is just a process in which a cell takes a bunch of low energy molecules, combines it with high energy source of light to produce even more low energy molecules, and an energy rich molecule. Think of photosynthesis like building a Jenga tower on vibrant table with just enough blocks to have one block left over after the tower. While the blocks are on the vibrating table, they are usually not exiting, with a very low chance of doing anything notable. However, with a lot of energy and patience, one could build a structure using the same ingredients that has spectacularly high chance of doing something notable, while the lonely leftover has even less a chance of doing something notable. The cell most achieves this effect through two processes: photophosphorylation and Calvin cycle. Joe Yoon out, baby.
First law of thermodynamics: energy cannot be created or destroyed, just turned into different types of energies. More often than not, the conversion occurs because the thing trying to use the energy cannot accept the type of energy that came within the package. And phosphorylation is exactly this process. Simply put, phosphorylation is how the plant converts the energy of the sun in the form of light into a usable form that is exactly used and transported by the plant. It achieves such a goal by utilizing the power of the sun to slap phosphates and hydrogen to various energies carriers of the cell. Now, let's see how that works. With the thylakoid membrane, there are these protein structures called photosystems. Photosystems are a complex mix of pigments and proteins that allow the plant to harness light and do things with said light. To maximize the amount of light collected, there are a group of colors from red, yellow, orange, and a few weird colors like blue and the king of them all, green. And with the power of these combined, they could tear up stable bonds and energize an electron better than Red Bull can energize our editor during the process of making this video.
So when a plant
is in sun's light, the photon hits photosystem 2, located on the thylakoid membrane, and activates it. As the protein system gets energized, it changes its structure in terrific ways. First of all, it shoots out 2 electrons from itself as the 2 particles are immediately excited by the photon particle. Then photosystem 2 proceeds to rip the electron out of a nearby unsuspecting water molecule and absorbs them for itself. Pretty metal. As the energized electrons are expelled from photosystem 2, they move at ballistic speeds until they are captured by the primary electron acceptor, which is a protein that specializes in catching high energy electrons. However, the ability to catch is slightly hampered by the primary electron acceptor's inability to hold on to the electron, as various electron acceptors play hot potato with the energized electrons, dissipating a bit of its energy as it travels down the steps of the electron transport chain. Although the energy isn't wasted, it is quickly used in attaching to the phosphate groups and to a local ADP to create ATP. For 1 electron, and on average, you can generate 1.5 ATP. After the electron transport chain, we come to photosystem 1, which repeats the process of launching the charged electrons from itself using the power of the sun and to be caught in the hands of the primary electron acceptor. It is at this moment that the electron has a choice to make, either to go back through the electron transport chain or to take part in a shorter chain of electrons which are passed through a combination of NADP plus and H plus to form an energy-rich molecule, NADPH.
The Calvin cycle is the process in which the chemically unreactive and useless carbon dioxide is turned into sugar. It is useful to note that since carbon dioxide molecules are pretty small compared to the glucose molecule, the Calvin cycle has to be repeated about 6 times before it can produce a full glucose molecule. Now for the steps of the Calvin cycle. First is carbon fixation. The carbon dioxide molecule gets married with the RuBP molecule with Rubisco as its priest and creates a PGA household. This process also gives the Calvin cycle its other name, C3 photosynthesis, because of the reasons that are on screen right now. The second step is reduction. You take the PGA molecule and you charge it with 2 ATP and 2 NADPH each. The 2 molecules deposit their energy-rich electrons onto the PGA molecules like Amazon addicts deposit their money onto Amazon. The analogy holds up surprisingly well, since with the electrons taken from the ATPs and NADPH, that PGA molecules evolve into G3P molecule, like how Amazon will soon evolve into being our supreme corporate overlord as it continues to take our money. The third step is regeneration. Even more ATP are utilized to turn, in the grand scheme of things, 10 G3P to 6 RuBP. Since the world sort of needs the process of photosynthesis to repeat from its first step, the original RuBP needs to be regenerated. And having the 10 G3P turn into 6 RuBP ensures that the process can continue on indefinitely. Finally, the bread and butter of photosynthesis, carbohydrate synthesis. There are a few G3P that are not used up in the regeneration process. These precious G3Ps are taken into a special place where they can be synthesized into any sugar the plant deems fit, with the same synthesis process being able to combine and create various saccharides and carbohydrates. Examples include the tried and true glucose, fructose, maltose. Even disaccharides like sucrose and polysaccharides like starch and cellulose are produced in this manner.